Hello all. So in the last sessions, we have seen the best practices in developing NLP applications, and we have seen how to we deploy and serve NLP application, and then we have started with multi-modal networks and image captioning, right? So we have seen what multi-modal deep learning is. We have seen what image captioning is with respect to image COCO dataset. How do we use this dataset for image processing? And then we have seen how do we process the image with CNN and ResNet, and also how do we use ResNet 50 for image feature extraction. So today in this session I would like to talk about the transformer model and how do we train the transformer model with visual encoder for image captioning or any other image related applications. Okay, so we have already seen transformer models in the last chapter, right? So the transformer model was inspired by sequence to sequence model, which has an encoder and decoder part. There are different types of transformer models. One BERT model, which is only an encoder based model. There are few transformer models which are based on only decoder, or few based on both encoder and decoder, right? So since the transformer model does not rely much on RNNs, the input sequences need to be annotated with positional encodings, which also we have seen. Okay, now annotating the input sequences with positional encoding, which allow the model to learn about the relationship between the input tokens that we are taking. Okay, now removing recurrence improves the speed of the model. Okay, all these things we have seen in the past chapters, right? So this innovation of the transformer model has led to the transformation or innovation to many large size models like BERT, GPT-3, etc. Okay, so when we talk about the transformer model, the encoder part of the transformer model will actually take the input, and the decoder will decode that particular output, right? So we will start with the modified version of the transformer model, and try to create a visual encoder, which basically takes the image data as input, and instead of text sequences it will take image data as input. And there are some other modifications that we do, because we have to accommodate images as input to the encoder part. Here we are not taking the sequence of tokens as the encoder part, but we are taking image to the encoder part. Okay, so we will see this particular transformer model that we are going to build. Okay, so the main difference you can observe here is how the input sequence is encoded, because here the input sequence is not the list of tokens, but here the input sequence is a image. Okay, so we will tokenize the text using subword encoder and pass it through embedding layer, which is trainable, right? So when training proceeds, the embeddings of the tokens are also learned. Okay, in this case of image captioning, we will try to pre-process the image into sequence of 49 pixels. So first we'll go for image pre-processing, each with an embedding size of 204, right? And this actually simplifies the padding the inputs, and all the images are pre-processed so that they are of the same length. Okay, consequently padding and masking are the inputs that you can skip. Okay, so in order to perform, see, the remaining steps would be same, using multi-head attentions, feed forward networks, encoder blocks, decoder blocks would be same, except that you're using image as input, and for pre-processing we use ResNet 50 model. Okay, so the following pieces of information is actually needed for you to implement or build the transformer model for image captioning. Okay, so first we talk about positional encoding of the inputs along with the input and output mask. Okay, our inputs are of fixed length, but the output and captions are of variable length, because sometimes depending upon the type of input, our output captions would be different. Okay, so this is one thing that we have to concentrate on. And the second thing that we have to concentrate is scaled dot product attention and multi-head attention. This will basically enable our encoders and decoders to focus on the specific aspects of the data. As you can see, I want to focus on only specific parts of the image, not the entire, because most of the image information would be relevant on the specific part. Okay, so for that we will use an encoder that consists of multiple repeating blocks, and we will use the decoder that uses the output from the encoder through its repeating blocks, as you can see here in the image. Okay, now when you want to implement the code for the transformer, you can take that directly from the TensorFlow tutorial titled Transformer Model for Language Understanding. Okay, you can use this code as the base and adapt it for image captioning use case. Okay, so it will be difficult for us to analyze the entire text now. So it will be briefly explain you the steps and procedures that we usually follow for adapting the transformer models from this particular TensorFlow library for image captioning or any other use cases that you want to work on. Okay, so one of the beautiful things about the transformer architecture is that we can cast a problem as a sequence to sequence problem and then apply it to the transformer model. Okay, so let us discuss about each and every aspect here in detail. First, let's talk about positional encoding and mask. As we know, transformer model does not use RNNs. Okay, now this allows them to compute all the outputs in one step, which will actually lead to significant improvements in speed and also the ability to learn long range dependencies, right? However, it comes at the cost of the model not knowing anything about the relation between the tokens. Okay, so for this reason we use a positional encoding vector with values for the odd and even positions of the tokens or the image pixels that we are taking as input to help the model learn the relation between the positions of the input. Okay, so that this will compensate the lack of information about the ordering of the tokens. When you talk about image captioning, this is important for captions. Okay, technically we don't need to provide this positional encoding for the image inputs, as ResNet 50 should have produced appropriate patches already. Okay, so in such cases when you are using a pre-trained model, you can simply avoid this step. Next, I would like to talk about scaled dot product and multi-head attention, as you have seen in the image above. Okay, the main purpose of this attention function is to match a query to the set of key value pairs. We know what attention mechanism is, right? So generating key value pairs, comparing them with the query using attention heads and generating the attention weights, right? So the output is the sum of the values weighted by the correspondence between the query and the key, and then we use multi-head attention, which learns multiple ways to compute the dot product attention and then combines this, right? So basically the scale dot product attention is computed by multiplying the query vector by the key vector. Okay, now this product is scaled by the square root of the dimensions of the query and the key. Okay, so using this formulation, basically we can compute the key and query vectors which will have same dimensions. Practically speaking, these dimensions of the query, key and value vectors are all set to the size of the embedding. Okay, we generally call this as D model. Okay, so multi-head attention basically concatenates output from the multi-scale dot product attention unit and then passes them through the linear layer. The dimensions of the embedding inputs are divided by the number of heads to compute the dimensions of the key and value vectors, and then this multi-head attention is implemented as a custom layer. Okay, so in this way this plays an important role when we design any other application using transformers. Okay, next, as you have seen in the diagram in the transformer model section, when you look into the encoder structure, okay, when you look into this particular encoder structure, the encoder processes the inputs with positional encoding and masks and then passes them through stacks of multi-head attention. As you can see here, stacks of multi-head attention and feed forward blocks. The implementation here deviates from the TensorFlow tutorial, as input is in the tutorial by default. Okay, now what we do is, in our case, we are passing 49 by 2048 vectors that are actually generated by passing these images through ResNet 50 architecture here. Okay, so the main difference is how the inputs are handled and how this visual encoder is built as a layer to allow composition into the eventual transformer model. Okay, so that is another important point that we have to understand. Okay, now visual encoder is basically composed of multiple head attention and feed forward blocks. We can utilize a convenience class encoder layer to define one such block. A stack of these blocks can be created on the input parameters and so on. Okay, next I would like to talk about the decoder. Okay, so the decoder is also composed of blocks just like encoder, as you can see here in the figure. Okay, each block of the decoder, however, contains 3 sub blocks. As you can see, the transformer in this particular diagram, you can see there is a masked multi-head attention sub block, and there is a multi-head attention block, and there is also a feed forward sub block. Okay, now here the feed, these 3 blocks. Okay, this feed forward sub block is identical to the encoder sub block. We just have to define a decoder layer that can be stacked to construct that particular decoder. Okay, so these three subblocks should be quite evident based on the preceding variables. Okay, so the first subblock, also referred to as masked multi-head attention, uses the output tokens. Okay, uh, all these three subblocks together can help you for decoding. Okay, and then after we study about decoder, we'll talk about transformer. Okay, once we are done with visual encoder, and decoder, the transformer is now composed of the encoder, decoder, and the final dense layer. Okay, as you can see here in the figure, the final dense layer is actually used for generating output token distribution across the subword vocabulary. Okay, so this is the basic architecture that we discuss about how transformer can be used for image captioning. Okay, simply understand, we take the image, use ResNet for pre-processing that image, use positional encoding, same encoder block, same decoder block, and the performance would be the same. Okay, now let's see how do we train the transformer model with visual encoder. Okay, so modeling transformer is different, training that would be another tedious task. All right, so the training the transformer model can take hours because we're dealing with images. Okay, so as we want to train for around 20 epochs, it is usually best to put into practice training the code into a file so that you can run from the command line. Okay, so note that the model will be able to show you good results after 5 or 6 epochs. Typically it starts from 4 epochs training. Okay, so when I talk about subword encoder, that also we can load it. You can load the training data. You can instantiate the transformer model. We will instantiate small model in terms of number of layers, number of attention heads, embedding dimensions, and then we will also instantiate feed forward units. For comparison, the bird model, if you take bird base model, it will be different. Bird large model, it will be different. So we give number of layers, D model, you know, and then dimensions, embedded dimensions. We will also give the number of feed forward units, and then we go for developing the model. Okay, so once you develop the model, it contains so many million parameters. Okay, and your model is ready for training. Okay, now once we are done with training the model, we will try to make some alterations to the model. One such alteration is custom learning rate scheduling. Okay, so we have heard this term rate schedule, which is identical to the one which is proposed in the paper, attention is all you need. If you read that paper, you'll understand what is custom learning rate scheduling. Okay, so basically when training starts, a higher learning rate is used as the loss is high. Okay, so as the model learns more and more, the loss starts decreasing, which requires a lower learning rate. Okay, so using the preceding learning rate schedule significantly will speed up the training and convergence. Okay, so we also need to loss to optimize, for which we go for loss and metrics. Okay, so the loss function is basically based on categorical cross entropy. It is a common loss function that we have discussed in so many other examples in the previous chapters as well. So in addition to the loss, and accuracy metric can also be used to track how the model is working on the training data set. So once you're done with custom rate scheduling and loss in metrics, computing the loss in metric, we can also go for checkpoints in mask. Okay, so we need to specify a checkpoint directory for TensorFlow to save the progress. We will use a checkpoint manager which will automatically manages the checkpoints and store a limited number of them. Okay, the checkpoint can be quite large. Basically 5 checkpoints for the small model would be approximately taking to 43 MB of space. Larger models would occupy more space. Okay, so once you're done with all this, we go for custom training. Okay, similar to the customization summarization model, we go for custom training. Okay, once you're done with all these procedures, okay, we will create mask for the input images, and the captions must be defined. Okay, so inputs are always of constant length, so the input sequences is set as ones. Only the captions that are generated by the decoder are masked. Okay, so there are basically 2 types of mask for the decoder. The first mask is the padding mask, since the captions are set to maximum length to handle 99% of the captions, which will work out on the generated tokens. Okay, and next we go for padding mask, which help to separate caption tokens from the padding tokens. Okay, so the second mask option that we use is look ahead. First is padding, and the second one is called as look ahead mask, which will actually prevent the decoder from seeing the tokens from the future tokens it has not generated yet. Okay, now once we are done with all this, we are ready to train the model and then generate the results. Okay, we are done with. So with this we are done with how do we use the transformer model, what is transformer model, and how do we use the transformer model with visual encoder for generating captions. Thank you.